And what's sine 90? 1, thank you. We don't want it to be 0 or else we wouldn't have any force. Okay, so QVB. And then that's also going to be equal to mv squared over r. So we've got v's showing up on both sides, so we could cancel one of those. And if we wanted to solve, let's say for the radius of rotation, you can move that to the other side, divide by these terms, and you'd have mv over qb equals the radius of rotation. And then we learned that the period of rotation for uniform circular motion was 2 pi r over the velocity. So you could plug in the r we just found. And the v's cancel. And so you get that the period of rotation would be 2 pi times the mass of that particle divided by its charge times the B field. So radius has units of meters, and period would have units of seconds, yeah. So, so those are the derived equations, and then of course if you needed frequency, that's just 1 over the period, or angular frequency, 2 pi times the frequency. So, as long as this is true, that the angle is equal to 90 degrees, then that particle will rotate in a flat plane forever and ever and ever, assuming that there's no frictional forces with air and stuff like that. So if it was in a vacuum, there would be nothing to slow down those particles, and they would just rotate forever. If for some reason that angle is not 90 degrees and you have to keep this sign of whatever angle it is, that introduces a component into our right-hand rule, and what you end up with is instead of that particle rotating in a flat plane, it starts rotating and translating. This is called helical motion. So that's what those photons from the sun are doing when they get locked on the magnetic fields of the Earth, is they rotate and translate. They create this helical motion down the magnetic field lines. I don't know if I included those equations anymore because it's a little bit niche, and I think there's like one example in the book where they deal with helical motion. So if you're interested, it's in the book, but I think I cut that problem out to save on time.
So for the future, when we're solving these problems, we just always assume that the angle is 90.
Yeah. Yeah, you guys won't see anything else. So, any questions about the equations? They're pretty manageable? Okay. Now the really cool thing, not to get too off topic, but if you had a particle come in, say you have a beam of protons enter a region with a magnetic field. Let's say what direction do I want my force to be? Okay, so a B field that's pointing into the page. You could tune that B field just enough so that as soon as that charged particle came in here and experiences that upward force, it could rotate a half circle and leave going in the exact opposite direction. So it would have translated a distance of 2r upward, but that could be a way to reverse the direction of your beam of particles if you're dealing with a particle accelerator, which probably most of you will never deal with particle accelerators, but there's good jobs at CERN if you ever want to work with a particle accelerator. Yeah, it would. Go discover the Higgs boson. All right, so it wouldn't be electromagnetism without introducing electric fields into the mix. So let's first talk about what would happen to a beam of electrons if you pass that beam through an electric field. So if you've got a capacitor right here creating a downward electric field, a beam of electrons is going to be attracted to that top plate. So as it passes through that electric field, it's going to be deflected upward since it's experiencing an upward force. Let's say you also add a magnetic field into your capacitor. So you got your capacitor plates like this, creating a downward electric field. And then you got two magnets, a north pole and a south pole, creating a magnetic field that points into the board. So these are X's, it's kind of hard to see. So your magnetic field is pointing into the board. So you take your beam of electrons, they're still going to be attracted to the upper plate with the electric force, but now, okay, so this is my velocity direction. The B field is pointing into the page. My magnetic force is pointing up, but of course it's an electron, so the magnetic force is actually downward on the electron beam. So a negative particle would be feeling a magnetic force that's downward that could potentially pull it down. In the case where it goes up, that would mean where the electric force is greater than the magnetic force. In the case where it's deflected down, the opposite was true. And if your beam passes through completely undeflected, then your magnetic force and your electric force are equal. So this is called crossed E and B fields, and it has a really useful purpose. Cathode ray tubes. And we don't use old tube TVs, but how many of you are old enough that you ever watched TV on a tube TV?
I still use one.
Okay. They're not that archaic, and many of us grew up with old computer screens, monitors that took up half the desk because they had cathode ray tubes in them. So how you're actually viewing something on those old tube TVs is with a crossed E and B field, and every image that you see is a beam of electrons that's getting painted across the screen line by line, and everywhere that those electrons go is by recalibrating the electric and the magnetic field so it goes exactly where it's supposed to go. Yeah, the physics is way more cool. So down here is where you've got your crossed E and B fields, and how those forces compare will dictate where those electrons end up hitting the screen here. So this is a little outdated. There's not a lot of uses for cathode ray tubes besides research. We don't use them in our everyday world anymore very often. But we do use them for research. So another term for the crossed E and B fields is a velocity selector. So what did they call this thing? Oh, I forgot there's a problem in your packet that gives us some background information on one of these doohickeys. Oh, Bainbridge mass spectrometer. So they utilize the velocity selector as part of their mass spectrometer. And the mass part of the mass spectrometer is that it's used to measure the mass of a particle. So the first thing is you want to select the same type of particles. So if you've got a source of charged particles, but you've got a bunch of different things coming out of here, so protons and electrons and other exotic particles that have a bunch of different masses, like alpha particles or whatever, you only want the same type of particles to leave. And your velocity selector, we said, a beam will go straight through if the force due to the electric field equals the force due to the magnetic field. And so this is the equation for the force due to an electric field. This is the equation for the force due to the magnetic field. They both have the charge in them, so that cancels. So the resulting velocity is E over B. But the charge has to be, the charge kind of plays into this. So if you've got different charged particles all coming through this same beam, some will have different velocities than others. They'll exit going at a different velocity. So, no, let's see. Well, this equation says the velocity is just dependent on the E and B field. So maybe they know, maybe they only send a certain type of particle through. That must be. Well, let's look at this example really quick since we're talking about it. This is example 27.6. All right, there's a whole bunch of backstory here. We don't really care about the backstory. So they want to detect helium plus ions. So they give us the charge of helium plus ion, which is the charge of an electron, and we're given the mass of that helium plus ion. They emerge from the velocity selector with a given speed, and then they're curved into a semicircular path when they enter a different B field. So they give B prime in that picture to show you that that's a different B field than the B field that was in the velocity selector. So the B prime is what's going to go into this equation after those particles with velocity start rotating. They're rotating using this equation. This would be the B prime. And then the velocity that it had, if you had to calculate that, the B in this equation would be the magnetic field that's inside the velocity selector itself, which is not necessarily the same. And then it shows how the particles will rotate into a semicircle and then hit a detector. So if you had different types of particles coming out of your source, then a heavier particle, once it exits here with a certain speed, and as I was muddling through this, the speed is based on the electric field and the magnetic field. It's not based on the charged particles itself. So any particles that you fire through here are going to leave with the same speed. But as soon as they enter that B prime field, the different B field, then their radius of rotation will be affected by their specific charge and their specific mass. So a lighter mass particle is going to rotate a shorter distance. A heavier mass is going to have a bigger radius, so it's going to rotate further, and it would be picked up further on that detector. So that's a way they can, one, separate out particles. I was just watching this on the Cosmos series. They actually used this exact thing to collect specific types of particles, so they have collectors at specific distances, and as it rotates through, the same types of particles will go into the specific collector for that type of particle every single time. So they can use that to grab specific particles, and they could also use this if they've got an unknown particle to figure out what its mass is based on the radius at which it hit the detector. So this problem is a little different because we're given the charge and the mass, we're given its speed, and we're given its radius, and we're going to figure out what the B prime field was that created that path for that particular particle. Okay, so if you guys want to try out example 27.6 for a few minutes, and if you guys are really not sure what they're asking, then I can do it on the board.
It's almost 11:40.
Yeah. Oh, hey, Chris, would you turn that video off?